Hello everyone, welcome back to my YouTube channel. This is Kripa K from Sri Venkateshwara College of Engineering, pursuing Computer Science and Engineering, currently in 6th semester. Today we are going to be dealing with the subject System Software and Compiler. Subject code 18CS61. In this video, I'm going to be talking about how to generate the object code for the following SIC source program and also how to write the object program for the given problem. The following is the mnemonics and opcode given for the particular problem. For SIC machine, we have four types of formats: type 1, type 2, type 3, and type 4. Type 1 as 1 byte, type 2 as 2 bytes, type 3 as 3 bytes, and type 4 as 4 bytes. Starting with the problem, firstly we need to generate the location counter. After generating the location counter, we can find out the object code and convert the object code to the object program. The operand value is 3000, so the first location counter value is 3000. So the first statement belongs to the type 2 format, so we need to increment 3000 with 2 bytes, so it becomes 3002. The next belongs to type 3 format, so we need to increment the location counter with 3 bytes, so it becomes 3005. Next we have plus LDB. Since there's a plus, it belongs to type 4 format. Since it belongs to type 4 format, we need to increment the location counter with 4 bytes, so it belongs to 3009. Base and total are assembly directives, so we increment the next with 3009. So the next belongs to type 3 formats, so we increment with 3 bytes for each. In the next, for the reserve word, we have one operand. One is equal to 3 bytes, so we increment the next location counter with 3 bytes. That becomes 3015 plus 3018. That becomes 3018. The next operand is 2000, so 2000 into 3 bytes, that is 6000. So we convert the decimal value to hexadecimal value. So we have 1770. So 3018 plus 1770 becomes 4788. Next we have 1 is equal to 3 bytes. So we increment the next location counter with 3 bytes, which we get 478B. So this is how we generate the location counter for each and every value. So these are the location counter for the given problem. Moving on to finding the object code. So object code for clear X, it belongs to type 2 format. The opcode is equal to B4. B4 is equal to 1011010. We take 8 values, so the opcode is shown as in the figure. We have two registers, R1 and R2. Since X is a register, the mnemonic code of X is 1. So we take it as 0001 and 0000. Grouping 4 each, we get the answer as B410. So this is the object code for the first statement. Going to the next, LDA hash 0. LDA hash 0 belongs to type 3 format. So the LDA opcode is 00. We take the first 6 suitable bytes for the opcode. NIXBPE. NIXBPE stands for, N stands for indirect addressing mode, I stands for immediate addressing mode, X stands for index addressing mode, B stands for base relative addressing mode, and P stands for program counter relative addressing mode, and E is set to 0 if it is type 3, and E is set to 1 if it is type 4. And displacement has 12 bytes if it's type 3, and address has 20 bytes if it is type 4. So for the given question, LDA has opcode as 00, and we take the first 6 bytes for the opcode. First 6 bytes for the opcode, and object code, we group 4 bytes each to get the object code for the particular statement. So the object code which we get is 010000 for the second one. Third instruction is plus LDB hash total. It belongs to the type 4 format. The opcode for LDB is 68. It is represented as follows in the binary format. So I is set to 1 because it is immediate addressing mode, and E is also 1 because it belongs to type 4 format. Grouping the 4 bytes, we get the object code as 69104788. For the fourth instruction, add table comma x, we have add table and x. It belongs to the type 3 format, and the opcode for add is 18, that is represented as 00011 4 zeros in the binary format. Since it is neither immediate or indirect addressing mode, n is equal to 1 and I is also equal to 1. And since it is index addressing mode, x is set to 1. So for B and P, we need to decide by finding the displacement. So the displacement is equal to 3018 minus 300C. How to find the displacement is, so for the given add table x, table is found with the location counter of 3018, and the location counter of the next subsequent instruction is 300C. So 3018 minus 300C is 00C. So the displacement is 00C. So grouping 4 bits, we get the object code as 1BA00C. Moving to the next instruction, that is TIX count. It belongs to the type 3 format. TIX has opcode as 2C. It is represented as 00101100 in binary. Since it is neither immediate or indirect addressing mode, N and I are set to 1. To decide whether it is base relative addressing mode or program counter relative addressing mode, we need to find out the displacement. So displacement of the instruction is, so count is has the location counter of 3015. So 3015 minus the next location counter of the given instruction, that is 300F. So 3015 minus 300F is equal to 6. So grouping the 4 bits, we get the object code for the current instruction is 2F2006. Sixth instruction is JLT loop. It belongs to type 3 format. The opcode given for JLT is 38. That is represented as 00111100 in binary. Since it is neither immediate nor indirect addressing mode, N and I are set to 1, and we need to decide whether it is base addressing mode or program relative addressing mode. For that, we need to find out the displacement. Displacement needs to be 12 bits. The displacement of the current instruction is given as, so the loop has the location counter as 3009, and the next subsequent location counter is 3012. We get the answer as FF7. If it falls in the range between minus 2048 to 2047, P is set to 1, or else B is set to 1. Since it falls in the range, P is set to 1. Grouping 4 bits, we get the object code as 3B2FF2 for the current instruction. Moving to the next instruction, that is STA total. STA total belongs to type 3 format. The opcode for STA given is 0C, that can be represented as 401100 in binary format. Since it is neither immediate nor indirect addressing mode, we can set N and I as 1, and we need to decide whether it is base relative addressing mode or program relative addressing mode. So to find out the displacement of the current instruction, the total as the location counter as 4788, and the next location counter is 3015. So 4788 minus 3015, we get it as 1773, where it does not fall in the range between minus 2048 to 2047. So since it does not fall into the range, we can take the value of base and total. So the displacement is 4788 for total. So total with the total value is 4788. So we get the displacement as 0. If the displacement had fallen in the value between minus 2048 to 2047, the program counter value would have been 1. Since it does not fall in the limit, base counter value is set to 1. So by grouping the 4 bits, we get the object code as 0F4000 for the current instruction. For the next 3 instructions, RESW1, RESW2000 and RESW1, we don't calculate the object code because those are the assembly directive. Coming to the last instruction, that is end. End is assembly directive and we don't calculate the object code, but we write the starting address for the end instruction. The starting address is 3000, so the object code for end is 3000. So this is how we find out the object code for each and every instruction by seeing which format it belongs to in the given 4 formats. After finding the object code, we can convert the object code to the object program. Object program consists of 3 parts: header record, text record, and the end record. Header record has the name of the program with 6 places, followed by the starting address with 6 bytes, and followed by the length. The length is found out by starting address minus the last location counter. Next is the text record. Text record, we can have 69 columns in the text record, each with 6 bytes, and the second is the length of the text record. The last is the end record. End record consists of the last address with 6 bytes. To find out the length, we can find out it by how many columns the text record has. So in this text record, we have 48 columns. That is 2 columns is equal to 1 byte. So 48 columns is equal to 24 bytes. 24 bytes, it is in decimal. So by converting into 24 bytes to hexadecimal, we have 18. So the length is 18 for the given object code. So this is how we convert the object code to the object program. I hope this video was useful in learning how to generate the object code and object program for the given SIC XC object program. Thank you.